And this is what I do to help me understand what's happening. I do a sketch. Okay? I do a sketch. And let's look at the force imbalance, the momentum equations, the first side. And I look from the side and I just show you a snapshot of a sinusoidal wave along gravity. Look at the shape of the sea surface. It's not fully correct here, the sketch, because you can see that the wavelength doesn't exceed the water depth 20 times, but this one is just for illustration purposes only. Okay? So you can see the sea level elevation. This is what we call eta. Okay? Let's activate the mouse is activated. Undisturbed sea level is this dotted line. Sea level elevation is positive in some parts, negative in other parts. Okay, and you can see that there is a slope in the sea surface. Okay, you have a positive slope or you have a negative slope. And under these pressure gradients, and the pressure gradients, the key here is that this pressure gradient operates from top to bottom. Okay, it comes from the sea surface, but in this shallow water example, it operates the same way from the surface down to the sea. No change from the surface to the seafloor. So over the entire water column, it accelerates the horizontal flow, either positive acceleration, okay, the UDT exceeding zero, or a negative acceleration, which means that this velocity component, the magnitude decreases over time. Okay, and this is what the impact on the velocity field. It's not a direct impact, it's an indirect impact, because what it does is it changes the existing velocity field, so there's some inertia involved. Okay, so this is the first one. So let's have a look at the second part. Let's have a look at what volume conservation. And in this example, we only look at a situation where the mean water depth is the same everywhere. It changes a little bit if you allow the total water depth to vary. Okay. Anyway, so again, I show you a snapshot. Okay, so it's just a snapshot that shows you horizontal flow structure. Okay, and you can see that there are some regions where you have a horizontal convergence. And I drew some vertical red dotted lines here so that you can imagine some sort of control volume. You have a control volume, you have a face on the left, a face on the right, and then you look at whether there's an inflow of volume, and if there's an inflow of volume, the sea level has to go up. Okay, so you can see there are zones where you have a flow convergence, pushing the sea level upward, and the sea level will increase over time. So this is the eta dt will increase over time. Or you have regions where you have a so-called divergence, where water is moved away out of your control volume. It's this part here in the middle. Water moves out horizontally, the sea level has to drop. Again, it is an indirect response, okay, because you get a change of the existing sea level, okay? So it can be negative or positive. It just means it will change. It will become more positive, or it will become less positive, and so, okay? So that's the thing. The other thing is, and I forgot to highlight that, is you have these two equations. There are two unknowns, sea level elevation and horizontal velocity component, but these equations are coupled. Okay, so there is an eta on the right-hand side of the first equation, and there's a u on the right-hand side of the second equation. Okay, there's also another eta on the right, hidden in the right-hand side of on the right-hand side of the second equation, because it's in this total water depth. This h here includes the average plus the sea level elevation. Okay, so it's not as simple as you think. So these are coupled systems. Okay, and it's relatively tricky to solve them. You can analytically solve this equation, and I will come to that. Okay.